Hey everyone, welcome back to Mind Maths with Amna. In today's lesson, we're going to go through the error correction model. Basically, what happens is that in time series analysis, many economic variables are in fact non-stationary, yet they often move together in the long run. When such variables are cointegrated, ordinary VAR models are no longer appropriate. And this leads us to the vector error correction model, which allows us to combine short-run dynamics with long-run equilibrium relationships. So let's begin. Suppose we have the long-run equilibrium relationship between y t and xt given as yt is equals to beta 1 plus beta 2 xt. Remember that yt and xt both are integrated of order 1, which means they're non-stationary variables. Okay, so if we define the long run equilibrium error as, basically this is the co-integrating residue. Okay, let's just call it zt, and let's define it as yt minus beta 1 minus beta 2 xt. Remember, this was the long run equilibrium relationship. Okay, this term measures the deviations from the long run equilibrium. Okay. So when we do the augmented Dickey-Fuller test, we assume that the variables under consideration follow a univariate autoregressive process. So what we assume is that zt is equals to rho zt minus 1 plus ut, and therefore change in zt is rho minus 1 zt minus 1 plus ut. So when we run the augmented Dickey-Fuller test, our h naught is that rho is equals to 1, which means that zt, which in this case is the long run error, is non-stationary. Okay, it's integrated of order 1. And if h1 alternative hypothesis is true, then zt is stationary, that is integrated of order 0. So when we reject h naught, it implies that in the long run the error is stationary. Okay, and whenever the error is stationary, we've already discussed it in the previous video, that when errors are stationary, that means that the variable yt and xt are co-integrated. Now that we know that they are co-integrated, we are interested in the short run and long run relationship between these variables. Okay, so let's do a little bit of algebra. Let's make this into 0.1. Let's make this into 0.2. Okay, so we know zt is equals to yt minus beta 1 minus beta 2 xt. Therefore, change in zt is going to be change in yt. Beta 1 is a constant, so there's no change there. Minus beta 2, change in xt. Okay, we want to substitute this back into the ADF regression. Okay, so this is the ADF regression, and I'm going to substitute this expression right here, and I'll get a change in yt minus beta 2 change in xt is equals to rho minus 1 into zt minus 1 plus ut. Okay, where zt was equals to this. Okay, so if zt is equals to this, if I lag it 1 period behind, then I'll get the value of zt minus 1, because I want to eliminate this expression. So a zt minus 1 will be a yt minus 1 minus beta 1 minus beta 2 xt minus 1. So I'll have then a change in yt is equals to a beta 2 change in xt plus a rho minus a 1 into a yt minus 1 minus beta minus beta 1 beta 2 xt minus 1 plus a ut. Okay, so this equation is the ECM. Let me actually highlight this because this is important. We can actually rearrange it so that we can write it like this, and this can come over here. Yeah, okay, so this is what basically tells us how y will adjust towards a long run equilibrium after any shock. Okay, so let's start labeling this. What is this is basically just the first difference of yt. Remember, yt itself is integrated of order 1. Therefore, change in yt is integrated of order 0. Over here, we have the first difference of xt, where we knew that xt is non-stationary and integrated of order 1. Therefore, change in xt is going to be stationary, that is integrated of order 0. This is white noise. Yes, it's integrated of order 0 as well. And basically this whole expression is the error correction term. Okay, which by the way we were labeling as z, right? And we said that the only way that x and y are co-integrated is when the error is stationary, right? So what we're asserting is that the value of rho is in fact less than 1. Okay, so if the value of rho is less than 1, then the error correction term denoted by zt, that is the which is basically the linear combination of y and x, is stationary, which indicates that x and y are co-integrated. Okay, so let's see what happens if there's any shock in output. So suppose y actually rises above the long run equilibrium, where this is the long run equilibrium. Okay, so if output rises above the long run equilibrium, then since the coefficient over here, since pi is less than 1 in order for x and y to be stationary, co-integrated, then the coefficient next to this term right here is negative, which means that any positive impact will lead to a fall in output, so that, for instance, you can draw a trajectory like this, that if there's a positive impact, then the change in y will be negative, so that it comes back to the steady state. that means the long run equilibrium. So this basically ensures, what you need to remember is that when x and y are co-integrated, that is the error correction term is stationary, then it ensures that after any if output deviates from its long run equilibrium level, then output will converge back to the steady state. So if there's a positive shock in output, then the change in output will be negative. Conversely, if output falls below the long run equilibrium, so if it falls below, since the coefficient is negative, this means that output will now rise back to the long run equilibrium. So the key result that you have to remember is that the augmented Dickey-Fuller test helps us establish the stationarity of the linear combination of y and xt, which we denoted as zt, which tells us that the series y and x are co-integrated despite being integrated of order 1. The stationarity of the error term ensures that they are, in fact, they do have a long run equilibrium, and therefore this tells us about the existence of an error correction model for any change in y due to any kind of error. Okay, so I hope this was easy enough to understand. So just for a revision, let's just do a question in this. You can actually pause the video, try to absorb what I've just said, and then you can solve the question with me. Okay, suppose you have a model which is given. So we're doing a practice question, and suppose they tell you yt is equals to delta plus theta yt minus 1 plus delta naught x1 plus delta 1 x t minus 1, sorry, xt minus 1 plus some kind of error vt, or let's call it, let's just leave it vt, ut doesn't matter, it's white noise. Okay, so first of all, I'll just give a recap. We know yt and xt are both non-stationary. They're integrated of order 0. But when we take a linear combination of them, let's call their error zt, and this is a linear combination of these two. Then if it follows an AR1 process such that it is stationary, then we can say that yt and xt are co-integrated, which means that they do have some kind of long run relationship. Okay, so in the long run, after a certain time, let's call it like after a certain time, there is no change in output, and there is no change in x, and there's no change, actually there is no error, so the error isn't there either, right? Because this is the long run. So for instance, you can say yt is equals to yt minus 1 and xt is equals to xt minus 1, and the error simply does not exist. If you want to give yourself a visualization, you can say, suppose there was a shock, it was moving, and after time t, y just became constant, so that yt minus 1 and yt, they're all the same after a certain point when you reach the long run equilibrium. Okay, when I substitute this into the model which is given to us, I'll end up with, well, let's move all of these are equal to each other, right? So I'll have a 1 minus theta into yt is equals to delta plus delta naught xt plus delta 1, let's just take it as common, delta naught plus delta 1 into xt plus vt. Okay, so therefore yt is equals to delta over 1 minus theta plus delta naught plus delta 1 over 1 minus theta xt plus vt. For simplicity, we can say beta 1 is equals to delta over 1 minus theta, and beta 2 is equals to delta naught plus delta 1 over 1 minus theta. So then we have the long run relationship between x and y, which is shown, actually the error is equals to a 0, so I don't need to add the error here because this is long run. Okay, so we have this showing us the long run relationship between these two variables. Okay, so now we want to see the dynamics of adjustment towards this long run equilibrium. Okay, so remember that let me just take this to the next page. Okay, so let's try to convert this into, we want to see how output will change, right? So I am interested in how output is going to change given the fact that any deviation, like any linear combination over here, like I said, zt, which is the error, yt minus beta 1 minus beta 2 xt, is integrated of order 0, where yt is integrated of order 1 and xt is integrated of order 1. So provided all of this, I want to see the dynamics, that how will output, I'm just instinctually saying how y changes. Okay, so let's subtract yt minus 1 from both sides. Let me tidy this up. Yt minus 1, I'll have theta minus 1, right? Yt minus 1. I want to have the change in x on the right side as well, so I can do this kind of manipulation. I can say delta naught xt minus delta naught xt minus 1, but I can't just randomly subtract something that will ruin the equality over here. So if I'm subtracting something, I'll have to add it as well. Okay, plus delta 1 xt minus 1 plus the error, which is in this question, it's a vt. Okay, so on the left side we have a change in yt. We have the delta plus theta minus 1 yt minus 1. Then we have delta naught change in x t. Okay, basically this expression. If I take delta as common, then if I take xt minus 1 as common, I'll get a delta naught plus delta 1 xt minus 1 plus a vt, right? Okay, so change in yt is going to be equals to, let's take theta minus 1 out as common. I'll get a yt minus 1. What do we have here? Plus delta plus delta 1 into xt minus 1. Oh, I took theta out as common, so I'll have to divide it over here. Yeah, don't make this mistake. Okay, and so basically this came here, this came here, this came here. Okay, this is left, this is left. Okay, plus delta naught change in xt plus vt. And what we can do is we can write all of this like this. I can put a 1 minus theta here, a 1 minus theta there. I'll let you know why I'm doing this. because I made a substitution earlier, which was that for simplicity, I assumed beta 1 is a delta over 1 minus theta. So the only reason I changed the denominator was so that I can use this beta 1 and beta 2. Okay, so let's rewrite this again. Okay, so this is beta 1, this is beta 2. I hope I'm not going too fast. Okay, beta 2 is over here. Yeah, done. Okay, so this is again the same conclusion as last time. Where was it? This is the error correction term. This is the error correction term, and this basically just tells us the speed of adjustment. Okay, so this expression, the coefficient of yt minus 1, simply tells you about it captures, you can say it captures the speed of adjustment towards the long run equilibrium. Okay, and this measures the deviation from the long run equilibrium. Should I write that down? Maybe I should, I don't know. Let me, this is the error correction term, which is basically telling us it just measures the deviation from the long run equilibrium. Okay, so I explained how this whole thing is the error, and we've just shown it using the ADF test that this is stationary, and therefore that implies that the coefficient next to it should be negative. Okay, so in order for us to have a model in which the level of output after any shock converges to the initial level, we need the coefficient next to yt minus 1, basically this whole expression, to be negative. Okay, so if yt goes beyond the long run equilibrium, then whenever theta minus 1 is less than 0, that is whenever theta is less than 1, then the change in output is going to be negative. Okay, so we get pulled, the system gets pulled back to the equilibrium, right? So therefore this indicates that we have co-integration between y and x. So whenever you get the expression here, one way to make this claim that to find whether two variables are co-integrated or not is just by looking at the coefficient, right? So suppose the examiner instead writes an equation like this. Suppose they write this coefficient as alpha, right? So they change this, they call this something else, doesn't matter. Let's suppose they call this lambda, they call this ET, whatever. Okay, so the way you can find out whether co-integration exists or not is, first you say that the error correction term, which over here is denoted by zt, is equals to yt minus beta 1 minus beta 2 xt, it should be stationary. And the second thing is that the coefficient of this error correction term, which over here is alpha, should be less than 0. So if it is less than 0, then whenever output goes above the long run equilibrium, then the economy adjusts itself back to the long run equilibrium. Okay, so this is 1 and 2 combined is proof that y and x are co-integrated, and the speed of adjustment and the way the economy converges back to the equilibrium can be seen through alpha. So basically the value of alpha tells you about the short run and also long run dynamics. For instance, even if in this equation or just this equation, if you want to see, if you only get this equation for instance, and they're asking you for the long run dynamics, you know that in the long run change in y t and change in xt is equals to a 0, right? So from this expression, when you substitute a 0 here and you substitute a 0 there, over here you get a 0 plus a 0 because the error is also 0 in the long run. You're going to simply be left with the expression yt minus 1 is equals to beta 1 plus beta 2 xt minus 1, and we know that's the same as yt is equals to beta 1 plus beta 2 xt because all value, there's no change in yt and xt. So again, this gives you the long run equilibrium relationship between these two variables. Okay, so that's it for the ECM. I hope this lecture and the practice question was beneficial, and if there are any questions you can ask me, and take care, and I'll see you in the next one. Bye.